Hi. For the final session for today, we're very happy to have Jim Halverson to kickstart this session.
Hi, everyone. Good. I can hear that my mic's on, so I'm not confused about that. And thanks to the organizers for the wonderful meeting. This has been a fantastic meeting so far. And, sort of ending the third day, thinking about what is it about. To some extent, it seems that one of the things that unifies the community these days is a love of field theory, like it always has, and applications of it in string theory, in gravity, even in condensed matter physics, and algebraic quantum field theory leading into connections with mathematics. And I'm going to add one more leg to that today, thinking about how field theory is related to machine learning. This is something that I got interested in 2019. Some friends and I held a meeting at Microsoft Research, and I'll tell you a little bit of that story throughout the course of the talk. And there's one result that sort of really hit home. And so all I hope to do in this talk is to convince you why some field theoretic notions appear very naturally in machine learning theory. And frankly, I think that there's not enough people thinking about that. Compared, for instance, when we use our ideas in condensed matter physics, there's tons of condensed matter physicists thinking about field theory, obviously. Far fewer machine learning people are doing that. And so I hope to give you a clear picture of some of the things that are happening, and also maybe a clear picture of things that are still to be done. So I am a PI at the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. We're doing many things, and we have a slogan, but roughly we're doing AI for physics and physics for AI. We're in the Boston area, headquartered at MIT, but also with a lot of contributions from Harvard, Northeastern, and Tufts. And if you're interested in connecting with us, you can check out our website. I'll mention it again at the end. We have a summer workshop coming up in August that will be lovely. It's at Northeastern this year. So I hope if you're interested in the things that I say today that you'll contact me or reach out or check out the website or something like that. So physics and machine learning has been represented a few times at this conference, and in some sense, when you look at the talk titles, this is going to be a session with numerous different ML applications. And most of the talks I've seen at Strings about it are sort of in the ML for physics direction. This is the usual fruitful applied direction. Bruno is going to talk about landscapes, and Vishnu is going to talk about Calabi-Yau metrics and Yukawa couplings. But one of the things that the organizers suggested that I might talk about is sort of the other direction, physics for ML. This is sometimes going by the phrase of physics of learning these days. I gave some TASI lectures last year on exactly this topic. It was very fun to tell students about it, and I encourage you to take a look at those if you're interested. But the basic idea is that I want to see the emergence of field theory language in this context, and then talk about what sorts of field theories are natural. Finally, this idea also gives ML-inspired approaches to field theories. There's a number of works in this direction, but one that has very thorough citations and a very long introduction is a paper from last summer with Mehmet and Anandita and Matt Schwartz and Keegan. And I encourage you to take a look at that also. So this is where I'm going to live today, these two lines. I'm not going to talk about applying neural networks trained on a computer to physics. I'm going to talk about the theory. So understanding machine learning is something, as it permeates our society more and more, that is a very important and interesting thing to do. It's also easier said than done. There's far fewer theoretical results than in our field, but there's still a growing corpus of them. And the perspective that I'm going to take today is that we need to understand deep neural networks. Deep neural networks are, if you haven't thought much about them, they're basically just functions, but in general, the deepness of them is the fact that they're compositions of simpler parameterized functions, and the parameters will sort of play a key role throughout. And so I'll explain to you why the parameters are so important in machine learning. So neural networks are parameterized functions, functions with parameters, and they're often very complicated if you write them as an equation. So this is the source of recent breakthroughs in ML, and we'll try to understand them. So here's a picture of something called a Kolmogorov-Arnold network, but lots of other networks look something like this. There's some sort of data that comes at input. This is actually a function on a computer. This is just a visualization of that function. And you can see that a couple of different things happen. There's some data that comes in. There's some structure to the network. There's some dynamics to the network. You can see it changing and evolving. There's little activation functions that are being learned here. There's some edges that are dying out because it's learned that for the problem at hand, they're not that important. But so this is some sort of dynamical function on a computer. And optimizing neural network learning, if we're going to take that approach to trying to understand machine learning, this is something that our community has already been doing for some time. Vishnu will talk about Calabi-Yau manifolds, and there's been also a community of people working on knot theory. That's very clean mathematical data that's good to try to understand machine learning with. There's also architectures that come out of this story. The one that I mentioned previously, but something that's also growing is something called geometric deep learning, where symmetries and other things play a really essential role. So for example, our friends in lattice field theory are using this and, for example, have SUN equivariant neural networks to try to do their best lattice QCD that they possibly can. Eva and company have something called energy conserving descent that they've been interested in for a while and working on. Bruno will mention that very briefly in his talk. And there's also other people doing interesting things as well that I'm happy to tell you about over coffee. One thing that might not seem obvious that will play a key role in this talk is the statistical nature of neural networks. And there's a number of people working on that as well. So the big takeaway that if you forget everything else from here on out is that I want to claim that in certain sense, certain language from field theory is also a natural language for understanding neural networks. So let's talk about that a little bit. And I think I started about 7 minutes late. So what does a neural network predict? So I want to say the obvious answer, and then I want to explain two complications with that obvious answer. So the network is just some function. I'm going to take scalars for simplicity. We're going to be talking about field theory. There'll be scalar field theories for simplicity, but the whole story goes through. And generally, these things theta, these will be the parameters of the neural network. And the simple answer is that for fixed inputs to the neural network, for fixed data and for fixed parameters, it predicts phi sub theta of x. And that is a true answer, but it's naive in the sense that it masks very important aspects of the neural network. First of all is the dynamics, that the networks evolve along trajectories in parameter space according to a fixed architecture data and optimization algorithm. And so there's some trajectory through the parameter space of the neural network such that as you take that trajectory, this function is updated. That updates the predictions, and it also, of course, updates the functions. So this network has predictions, but those predictions are evolving. And of course, that's what the learning part is. But the thing that maybe isn't something that as many people have thought about, it's not the obvious thing that we hear about when we hear machine learning, is the statistical angle on things. So this squiggle in statistics means drawn from. And what it means is that when you start your computer and you have your neural network on your computer, those parameters are drawn from some distribution on parameters. I'll call it P of theta throughout this talk. And so in particular, one of the things that you might realize when you think of that is that any given neural network, the first time you fire up your computer, is a random function. And a random function isn't fundamental. It's the ensemble of functions that is more fundamental. And so what you might do is you might compute the one-point function, or average prediction of the neural network. Or you might predict the two-point function, which is the covariance of the neural network predictions. And those are natural things that are arising in this context. So the ensemble of neural networks is important. Of course, the dynamics and the statistics go together. If you were to really not worry about computational cost, the thing that you would want to do is sort of train all of the neural networks, start them all, let them all evolve, and what you'll have is an evolving ensemble of neural networks, and their predictions evolve. That's a time-dependent one-point function, and their variance evolves also according to a time-dependent two-point function. And one of the things that's interesting about this is that putting this dynamics and statistics together, there are contexts listed here in which people have a pretty good understanding of the evolving one-point functions and the evolving two-point functions of an infinite ensemble of neural networks as they train. And so all I'm trying to point out here, and with this big point that field theory is a natural language for machine learning and for neural networks, is that the network prediction matters, but really the ensemble network prediction is some sort of one-point function that's time evolving. Okay? So I'm happy to tell you a lot about those theories, but it's not quite as relevant for the details of this talk. So that's the idea. The recap is that understanding neural networks is essential to understanding machine learning. There's an ensemble of them, and they're evolving. How does the average prediction evolve and the covariance? These are questions about learning time-dependent, that T is the learning time, time-dependent one-point functions and two-point functions. And if you're going to use that field theory language, you could ask, do these field theories satisfy any of the properties that we know and love in field theories that we study? Or alternatively, if they don't a priori, you could say, can I engineer my neural network structure to get them to satisfy some of the properties that we love? Okay, so here's the outline of my talk. I'm going to tell you a little bit about this story, about this thing that I was surprised by at this meeting in 2019 at Microsoft. I just already gave this intro part. And I like to think of this as a physics surprise from ML theory. And it's not so surprising in retrospect, but it's an important point in the history of this subject. And then once I have this surprise, it'll suggest maybe trying to build up a more general dictionary between understanding neural networks and understanding field theory. And so I'll give you some generalities, and then I'll talk a little bit about symmetries. I'll talk about the origin of interactions. And then, because we're physicists, I'll mention a little bit about conformal symmetry and also about unitarity. Okay, so let's get started. The first thing that I want to tell you about is about how free theories arise with neural networks. And this is this fact that I learned in 2019. So the first example of this is what's called an infinite width single layer network. This is a result due to Neal in the 1990s. Now I'm actually giving you a function. The neural network is a scalar on some d-dimensional Euclidean space. And what we do is we map it up into a higher dimensional space n according to some matrix of parameters, W0 here. And then there's a nonlinear function sigma here that acts element-wise on this n vector. And then we have this matrix, this vector here that projects it down to a one-dimensional space R. So this is the function that I'm considering here. And what Neal taught us, there's a small typo on the slide, but I won't worry about it, is that because this sum here in this function, this is an n vector and this is an n vector, and they're getting dotted together, that as long as you make appropriate assumptions about the n scaling, that in the n goes to infinity limit, these neural networks as random functions are drawn from generalized free field theories. So there is something about neural networks that is directly related to generalized free field theories in the large n limit. So the mechanism is simple. This is, of course, known to our friends in machine learning, but they like to study many different architectures, and sometimes this point gets obstructed. So an architecture is just basically the way that you form your neural network. It's the type of function you write down, and in that structure of the function, you put your parameters in certain places. Here, I'm going to imagine that I have a bunch of parameters in these functions here, and I'm just taking a large n sum. And as n goes to infinity, if these neurons are IID of any architecture, then as n goes to infinity, what you have is a Gaussian theory. That Gaussian theory is a generalized free field theory with some operator that's the inverse two-point function appearing in here. And the fields, of course, are Gaussian distributed by the central limit theorem. One thing that's true about these theories that I mentioned during learning is that sometimes this Gaussianity persists during training, but there's very crisp ways in which we know that that's suboptimal. But there are theories that remain GFFs for all time. But the other point about this is because this is the mechanism, in these architectures, there's sums appearing everywhere. So for example, this type of network here, this parameter n is called the width. This is called the depth of the network. And this is a function that tells you how you go from the elf layer to the elf plus first layer. But these sums are basically giving you central limit theorems at each individual layer. And so in particular, these deep, fully connected networks, which are the non-trivial depth generalization of the one on the last slide, these are also Gaussian distributed at large n. Transformers, which underlie large language models, GPT, et cetera, those are also Gaussian distributed at large n, where n is the number of attention heads now. And similarly, convolutional neural networks, which are good for images, are Gaussian in the number of channels goes to infinity limit. So that is sort of just the fact. This is everywhere. It's due to the central limit theorem. And so somehow this large n limit might be relevant for understanding aspects of neural networks. Finally, one thing that was taught to us is that these generalized free field theories, in a paper in 1996, Williams showed how to compute with them. Computing with these infinite networks is done by doing an appropriate integral in parameter space. And we'll have a lot more to say about that. Good. So with the time that I have remaining, which is about 10 minutes, I'm going to tell you a little bit of the things that come out of developing this story: generalities, symmetries, interactions, and a little bit about conformal fields and also unitarity. So the generality is the following. Just to repeat, a network is some parametrized function with parameters theta. At initialization, these parameters are drawn from some distribution p of theta. And so in particular, this defines correlators, where you compute the correlators in parameter space. This is the way that Neal computed the two-point functions in his theories in 1996. And so given those statistics, you can compute correlators, and you can add dynamics for learning. This sort of suggests a more general formulation that the essential data that comes with specifying this neural network is the architecture. This phi sub theta is just the structure of the function and the associated parameters that appear in it. But you don't just specify that, you also specify p of theta, the distribution on parameters. And given this distribution on parameters and the architecture, you can write down a partition function of this form, and you can compute correlators in the normal way. And in some cases, you can even relate it to an action-based description. But part of the point, and this is what Williams was doing in 1996, part of the point is that you can do all of this here even if you don't know the story here. In his large N limit, he deduced by the central limit theorem that he actually had a Gaussian theory, but he did all of the calculations of the two-point function in this description. Good. So how do you do symmetries in this setup? You do symmetries by showing the invariance of the partition function. It's a very simple mechanism, but I'll explain it. You transform the field according to the transformation that you would like to do. Very regularly, depending on the architecture, you can absorb that transformation into the parameters, and you can redefine the parameters in the partition function. And what this gives you is some transformation of p of theta, but if p of theta is invariant under that transformation, the whole theory is invariant, and you have global symmetries for this neural network. So examples of this, space-time symmetries are symmetries on the input of the neural network, because that's the analog of x. Phi of x is my Euclidean field, so the internal symmetries are symmetries on the output, and you can engineer all sorts of different things. In particular, you can engineer full Euclidean symmetry so you get translations and rotations. Just to give you an example, the way that rotation invariance arises via this mechanism is very simple. Here I have my architecture. This is literally anything. This is any neural network attached at the end of an input neural network where all of the structure related to rotational invariance comes from here. So this could really be anything. The parameters are these w's and these theta g's. And basically, if you do a rotation on x and absorb it into a redefinition of w, and the w distribution is invariant, for example, if it's IID Gaussian, this is an invariant distribution, then the partition function is invariant. And when you go to compute those correlators, you see that it actually has the symmetries that you demand. Okay. But the nice thing about this trick is this is a trick for seeing the symmetries without having to actually evaluate the integral. Okay. Good. So interactions. So in this setup, the central limit theorem is the reason why we have free theories as n goes to infinity. And so what you might imagine doing, and this was sort of one of the buzzwords that was in the air in 2019, is to ask the question, what are the sorts of interactions you get at finite n, and how do you characterize them? The right way theoretically to think about that is, because you're getting the free theory from the CLT, parametrically violating its assumptions is a way to turn on interactions. So in particular, as n goes to violate the n goes to infinity assumption, but you might also say that you're going to violate the statistical independence assumption, which is another one of the assumptions of the central limit theorem. So the interactions, for example, when you normalize this way, you can show that the connected two-point functions exhibit, of course, typical CLT behavior. This is just a CLT result, that the connected correlators die off in 1 over n. The Edgeworth expansion gives you a way to compute the action at leading orders in 1 over n. This is a method from statistics that gives you ways to expand around Gaussian fixed points. But you can also do this other thing where you turn on some interactions from independence breaking. So just to give a sense of how this goes, I'm going to take my previous example that I had for the rotation symmetry. The previous example that I had, this is any neural network appended to just some simple input where I have these weight matrices acting. The previous example I had was the lambda goes to 0 example, but when you turn on this lambda non-trivial, what you find is that you preserve rotation invariance in theory, but this actually turns on interactions because you can no longer factorize this probability distribution. The statistics of these parameters are correlated. And you can do perturbation theory in lambda. Good. We have an example where we engineer a free theory. It gives a power spectrum for the two-point function that's 1 over p squared plus m squared. It's the free scalar. And in this context, you can ask, if you get the free scalar, how can I get phi-4 theory? The way that you get phi-4 theory is you do the operator insertion into the partition function. That would be the natural deformation to turn on phi-4. But then you need to interpret that somehow in this new context where we interpret the neural network field theory in the context of this parameter density. So what happens is when you induce this operator, it induces an effective deformation of the density on the parameters. And this deformation of the density on parameters gives you independence breaking. So in this case, we have 5-4 theory described by an infinite width neural network with a different description than we normally use, where we have these parameters. And the local interactions arise from the breaking of statistical independence. Okay? So that was the CLT assumption that we violate there. Finally, 2 more things. We can do conformal symmetry. We can generate conformal fields. So Lorentz transformations in d+2 dimensions induce nonlinearly realized conformal transformations on the d-dimensional projective null cone. This is a standard fact in CFTs that many of you use. And the basic idea that we had in this paper with Naskar and Tian was to define a Lorentz invariant d+1 dimensional theory of homogeneous fields, to do computations there, and then to push down to the projective null cone and see conformally invariant correlators. There's 3 key principles there. Lorentz invariance comes from the previous mechanism. You have to ensure that your correlators are well behaved. But here's the thing that the neural networks sort of get you for free is homogeneity. You're specifying the class of functions that your theory is described by, and we demand that it's a homogeneous function. Okay, just to give you a quick example of that, there's a trivial pedagogical example that makes the point. If you just let the parameters be capital theta, and the architecture is theta.x, and theta is rotationally invariant, this gives you a Euclidean theory that when you Wick rotate, turns this Euclidean dot product into Minkowski, and you get a 2-point function here and a corresponding 4-point function that is Lorentz invariant, such that when you push down to the projective null cone, you get conformal invariance. And so in particular, we have the exact 4-point function in this theory, and we know a little bit about this theory. Finally, you might ask the question, I'm trying to develop some sort of dictionary between neural networks and field theories. When are these Euclidean field theories quantum field theories? This is, because they're Euclidean, you can rely on classic things in the constructive quantum field theory literature. One of them is known as, one of the key results is known as the Osterwalder-Schrader reconstruction theorem. And constraints on Euclidean correlators in that context, the theorem goes, is sufficient to ensure that you have a nice Lorentzian QFT. So in particular, the axioms include Euclidean invariance, permutation symmetry, the cluster property, cluster decomposition, and something called reflection positivity, which is the key thing in this reconstruction theorem for ensuring unitarity of the theory and absence of negative norm states. So this is also something that appears somewhat regularly in our community, reflection positivity, and we want to ask how it arises in a neural network context. So in particular, 2 facts about reflection positivity that you should know is that Gaussian theories are pretty easy to check because all of the correlators are determined by the 2-point function. And in particular, Lagrangian deformations of RP theories are reflection positive by an appropriate perfect square mechanism. And that's why we don't worry about this for Lagrangian theories. But outside of these cases, we're looking for a more general mechanism to get unitarity. So there is a particular way to take this general way of writing reflection positivity, and this is how we express it in a neural network context, where now our expectation is computed by integrating against a parameter density for the neural network parameters. And if you can split the parameters in such a way such that the density splits in this way and a certain condition is satisfied, this sort of splitting of the parameters, which you can do by fiat, because you get to define the theory and the architecture, gives you a reflection positive theory. So this is something that's work in progress with Christian Furco, partially because I know I'm nearing the end of my time. I don't want to go into too many details. But we're connecting with the stochastic process literature and trying to understand generally, both in quantum mechanical settings and in quantum field theory, how unitarity arises here. So there's a wide class of models, it seems, and we're still exploring. Good. OK, just to recap, I told you about field theory for neural networks, and hopefully I've convinced you that this is a natural language. I told you about this physics surprise from ML theory that at large n, these neural networks are drawn from they're drawn from Gaussian distributions. They're generalized free fields. Then I told you a bunch of things about generalities, symmetries, interactions, conformal fields, and unitarity. Some of the things that we would want to do anytime we're trying to connect field theory to something else. So this is sort of the outlook that we're developing some of this formalism, and we're hoping that we can go both directions here. This talk, in some sense, was mostly about developing field theory from a neural network perspective, using cherished physics principles, and I'm happy to give a little bit more of a physics outlook on that. But I was asked to comment potentially on some machine learning outlook, And so I'm going to do that. So one thing I want to emphasize is that the current iteration of large language models that you hear about are enormous and they are expensive. And only about 5 companies in the world can train full-scale large language models because they cost millions and millions of dollars. Therefore, sparsity, which is a subject in machine learning theory, which means the development and understanding of small but powerful neural networks, is an extremely important direction. This is actually relevant for LHC. I'm happy to tell you about that too. And the basic idea of sparsity is this. What you would like to be able to do is have some complicated neural network like this. By the construction that I've told you, I have a field theory here, and a field theory here, and a field theory here, and a field theory of the network at output. And I want to try to understand those statistics and dynamics. But something else that you want to do is you want to be able, ideally, to turn this network into this network such that you can train this one and still have it be really good. And the reason you want that is because you would like to get these techniques to broader communities and not just put the training of large language models in the hands of big companies. And that's a good question, but this is a hard story. One of the questions that you might ask is whether you can sparsify the models and still retain powerful approximation theorems, but in a way that retains these theoretical guarantees. If you do this, you might expect that the network might become bad. And what this Kolmogorov-Arnold story that I mentioned very briefly at the beginning does is it uses the Kolmogorov-Arnold representation theorem to motivate a new neural network architecture. And one of the stories that is true, but not so much in the literature, is that you can think about this Kolmogorov-Arnold network, which has a theoretical guarantee, as a sparsification of a much larger network that also has a theoretical guarantee. So this is just a fact about this structure. And basically, I'm proposing that architecture design is, I'm telling you, it's not a proposal, this is a known fact. Most of the progress in machine learning in the last 5 or 10 years has come from breakthroughs in architecture design. Something that we need now is architecture design while preserving sparsity, while having small neural networks. I'm imagining that we might have a setup where we can use these field theory ideas to understand the field theories on the different sides and hopefully get some sort of sense of how these ideas motivate new architectures. So that's a machine learning outlook. I'm happy to talk more about that, but that's something I'd like to try to do myself in the next couple of years if no one does it first. Finally, to wrap up, we have a lot of meetings coming up this year. If you're interested in getting involved in this area, we have the IFI Summer Workshop in August. String data is continuing to be in very fun locations. The last couple of years were Cambridge, Caltech, and Kyoto, and it's going to be back in London. There's a new Cambridge Infosys AI lab, and it's also going to be at the London Institute of Mathematical Sciences. String Pheno 2025 is at Northeastern in July. And finally, there's a KITP program on generative AI for high and low energy physics that we're running this fall. We hope you'll join us. Thank you very much. I hope I didn't go over time. Thanks.
And for that beautiful overview. Questions, please.
Hi, thanks for the nice talk. Do you have anything to say about RG flow? Is there some nice picture in terms of this? Does it have anything to do with sparsification, or is it completely different?
Yeah, so there are definitely ideas along those lines. One thing that sometimes people tend to do is call any flow an RG flow, and I try to avoid that. But there's a classic paper from 2014 due to Mehta and Schwab that had to do with moving down the network and thinking of that in RG flow language. You could probably marry that with the sparsity idea. In these other contexts, like for example, when I engineer standard 5-4 theory, the cutoff appears in a particular place in the neural network description, and so those sort of stories enter. But there's a number of papers on RG in this story. I'd recommend work by Mark Klinger and David Berman, and also a recent paper by Miranda Cheng and Mathis and Max Welling. Yeah.
Thank you.
So what, if anything, would go wrong if on the neural network side you violate reflection positivity?
Nothing. So
nothing. Okay.
Nothing. And to say this super clearly, I'm just building things up here according to things we love. These stories all already appear in machine learning theory literature, nothing to do with physics. To my knowledge, conformal symmetry doesn't. Dan and Shou in their book wrote something about scale invariance, but not full conformal symmetry, and unitarity is nowhere to be found in that literature. So these are things we love that are not yet too much in the ML literature. Yeah.
Okay, thanks.
Yeah.
Maybe just one more question in light of the time.
Okay.
Yeah.
So I have a two-part question, but even if the first part is wrong, please answer the second part.
Okay.
Would it be an oversimplification to say that what you were doing was you're given some action and you do a field redefinition so that the action becomes Gaussian, and then the neural network has to learn the details of the field redefinition. So rather than having the interesting part in the action, you put the interesting part in the field redefinition.
Mm-hmm.
I'll just ask the second part, even if this is not
Sure.
accurate. I didn't understand what we really learned about the field theory by looking at it this way. I saw you gave the example of the homogeneity, which came for free, but that's kind of something that's simple to get.
Yes.
So what did we really learn from the field theory by looking at it this way? Is the claim that this is a better way to do lattice calculations by doing this, or why should we really
You are
look at
mentioning,
field theories?
yeah. Thank you for the questions. You're mentioning too many interesting ones, but I'll try to get to all of them. Let me go back to the slide where I mentioned homogeneity. First, I'll come to your point. People don't do this in machine learning, but you could define a complicated one-parameter neural network, and all of your correlators would be a normal single integral. That is rather different from a path integral. And so if you computed the action associated to that, it would be wildly non-Gaussian in general and probably very hard to determine. The second question was about the homogeneity. So what we proposed in this paper was basically a new construction, as far as we can tell, of conformal fields. How they fit into full conformal field theories is another question. But basically, as far as I can tell, in the embedding formalism literature that's all over the Bootstrap, it's mostly used to understand conformal kinematics. It is, as far as I can tell, not used for construction. So what we're proposing is that you define a Lorentz invariant theory in D+2 dimensions, that is not translation invariant, because the translation invariance of the Euclidean CFT comes from the higher dimensional Lorentz symmetry, and you do the story upstairs, and then you push down to the projective null cone, and you get conformal invariance. That's what we did in this example. And so basically what the homogeneity was buying you was a way to define an appropriate D+2 dimensional Lorentzian theory such that you could push down to the PNC. So we are hoping that it's a new construction of conformal fields.
These are not local CFTs, right? Why would you expect these to be good local CFTs satisfying the bootstrap constraints?
Yeah, good. I am claiming that they give you conformal correlators, and we can even compute them in certain cases. And to get extra normal properties that you might care about, for example, unitarity, you need to do more. So the basic construction doesn't even get you unitarity. That's extra stuff you would have to put in. Thank you. Oh, and lattice you asked about also. I also hope to do lattice, but let's talk at coffee.
Great. Let's thank Jim again and move on. Thank you very much. So next we're happy to have Bruno De Luca, who's going to tell us about landscapes.
Okay. Thank you, and let me also thank the organizers for this great conference and for the opportunity to speak here. So today, indeed, I will be talking about landscapes, and in particular, coming from the study of the Sitter landscapes. So as we know, constructing accelerating cosmologies in UV complete theory of gravity is an important but hard problem. And our community has approached this problem from different points of view. You can start studying explicit construction or statistical studies thereof. You can, for example, ask what are general properties, like conjecture what's allowed and what's not in UV complete theories. Or you can, for example, use an holographic approach. And for this, I encourage you not to miss Gonzalo's talks tomorrow. But I would say that regardless of your point of view, I think it's important, it could be useful in any case, if we can construct explicit construction as simple as possible. And in particular, in this talk, I will describe some ways we can construct the Sitter cosmologies, the Sitter spacetimes in string ORM theory, away from more traditional corners of Calabi-Yau compactifications. And specifically, I will first review a proposal that we put together with Eva and Gonzalo for constructing the Sitter spacetimes in M theory. And in doing so, I will present some work in progress along these lines, where we are making this proposal more precise in the sense of constructing explicit families of manifolds, and so associated de Sitter construction in which you can estimate various physical quantities. And then, in the spirit of this session, we will switch gears a little bit, and ask the question of whether it's possible or not to use machine learning methods, for example, to directly solve the equations of motion for general compactifications and then find the detailed metric more generally than what we know is possible, for example, for the Calabi-Yau case, as we will see later from Vishnu. And in doing so, I will review briefly how this works and the fact that we can often use physics methods to perform this kind of computation. And then I will comment on a toy problem I studied recently on using machine learning to construct these metrics on the hyperbolic manifolds that we will see, and that has application for the sitter construction I will review now. So let's start with the sitter 4. So whenever you have a theory with exact dimensions, one of the most important things you have to do is to stabilize the volume, meaning the volume of the extra dimension is a field that you need to find a potential for it. Specifically, if you're looking for the sitter vacua, you will like a potential with a positive minimum. And the simplest structure you can have, the simplest structure is the one here in the slide, which this is called sometimes a three-term structure. And an important feature is that you need some negative contribution to the potential. You need some sort of negative energy, which is needed also to evade standard no-go theorems that forbid the sitter spacetimes in higher dimensional theories unless you have it. And there are various ways you can think of negative energy contributions. One popular choice is the use of orientable planes in string theory, but another that I think is quite natural is the use of quantum effects. And I think this is natural because whenever you are breaking supersymmetry, for example, if your internal space has certain small cycles where you impose antiperiodic boundary condition for fermions, you break supersymmetry, and so you generate generically some zero-point energy. And in particular, you will generate, in this case, some Casimir energy that can be negative, and it is negative in this case. And so this can be the negative energy contribution you can use to stabilize the volume. And more generally, this has been used also in other contexts, for example, for compactification of the standard model from 4 to 3 or 2 dimensions, or for the construction of traversable wormholes. And you can compute explicitly the form of this Casimir energy in the approximation where you're considering these small cycles that will size very slowly. And in this paper with Ivan Gonzalo, we propose indeed to use Casimir energy as the negative term in the potential. And then as the two other terms, the two classical terms that contributes positive to the potential, we propose to use, we are working in M-theory, and we propose to use the homogeneous configuration for the M-theory flux in internal space, the F7, as well as the other contribution will be, in this case, a negative curvature. And the curvature has to be negative to contribute positive to the potential. And in addition, since Casimir energy is we're not assuming some global circle where this is supported, but it will be localized in certain region of the internal space. This means that the internal configuration will not be homogeneous, and a warp factor will be also generated. And this means that we need to be a bit more precise and work with an effective potential that includes the effect of the warping, as it was derived by Douglas in 2009. And this means that the curvature will actually get a contribution from the warping. So the important term is the negative curvature corrected by the warp factor. And we will see this a bit more in detail. So this is our proposal of ingredients such that in M-theory you can get the sitter. And of course, with such a proposal, if you want to make it explicit, you need to satisfy certain conditions, certain consistency conditions. First of all, we are assuming that we have negative curvature and these small cycles, and we need to make sure that manifolds that have both exist. And second, we don't want to need cycles that are too small, in the sense that we need these quantum effects to build up in these regions, but we want to be, if possible, parametrically away from the danger of requiring sub-Planckian circles, because then we will lose control of low energy approximation. We will need to start worrying about non-perturbative effects, and this will be harder to control. And finally, of course, in such a configuration, once we build it, we need to make sure it's self-consistent and it solves the equation of motion self-consistently. So let me now briefly review how we address this point in our earlier work. So first of all, negative curvature and small cycle, they go very well together. In particular, you can think of hyperbolic manifolds, which are manifolds that have constant negative sectional curvatures. And these manifolds generically have some local regions depicted here in the slide, which are called cusps. In these local regions, there is some torus, some local transverse torus that is slowly shrinking. And this is where the quantum effects in the form of Casimir energy will build up. However, a cusp is not yet good enough for our purposes, because a full cusp becomes slowly shrink to 0 size at infinity, and so at a certain point it becomes of Planckian scale, and we will lose control of the non-perturbative effects there. But luckily, there is a beautiful mathematical construction that tells you that you can start from hyperbolic manifold with its full cusps, and for each cusp, you can perform the following procedure. You can select a closed geodesics in the cusp, and you can attach to it a solid torus. This procedure is called filling, and once you do that, you are basically killing the geodesics, and you're left with a local n-2 dimensional torus, whose size now, that now shrinks up to a finite size, and you can control this finite size. You can control it in terms of the length of the closed geodesic you started from, and you can do this procedure independently and for all the cusps simultaneously. And once you do that, you are left with a compact manifold, which in general, in dimension greater than 3, is not hyperbolic anymore, but it's still Einstein and still of negative curvature. So it's still good for our purposes. And another important property of such manifolds is that they are rigid. And this means that once you have fixed the volume, there are no other moduli. There are no massless deformations of the geometries. And as you can imagine, this is important for phenomenological purposes, because since here the problem of moduli stabilization is much simpler, because you don't have all these moduli to starting from. Now, then we need to solve the equations of motion on these manifolds. And as we'll discuss a bit more in detail later, this is a hard problem. These are Einstein-like PDEs and internal dimensions. But luckily, there are different approximations you can use in different regions to simplify the problem. And so let's start looking at the cusp regions. This is, in a sense, the most delicate part, which is where you need this local competition of the quantum and classical effects. But luckily, there is a simplification here, which is that in these regions, most of the dynamics only depends on the radial direction on the cusp. And this means that you can reduce the full set of 11-dimensional supergravity equations, including the flux and Casimir. You can reduce this full set of equations to a set of ODEs, which you can then integrate numerically. And what you see in the slide is indeed is a numerical solution of all the equations of motion. And what you see there is that there is a cycle, one cycle that is shrinking smoothly, up to like in the field geometries. And there is a 5-dimensional local torus that is slowly shrink up to a finite size. And this is where the Casimir is supported. And indeed, in the equation of motion, the Casimir on this torus is included. And finally, there is also a warp factor, which is non-trivial and varies according to the equation of motion, as we have anticipated. And this is a local solution. And what we discuss in the paper is that you can be in a parametric regime such that you can then glue this local solution to the bulk of the manifold, such that the corrections to the hyperbolic metric in the bulk are subleading in this parametric regime. And what I want to discuss now is how to make these conditions about the gluing more explicit in such a way that you can then estimate various physical quantities for these compactifications, such as the cosmological constant. So summarizing, the picture to have in mind is the one in the slide. We have these manifolds where there are these cusps. And in the cusp, we have already solved the equation of motion. And we are imagining of gluing this cusp to the bulk of the manifold. And to do so, we need to solve the equation of motion and have the conditions that impose global consistency of these configurations. And let's have a look at this equation of motion. So one class of equation of motion you get is when you vary the action with respect to the internal conformal factor. And you get the equation in the slide. This is an equation that fixes the Ricci scalar of the internal metric in terms of the other physical sources, such as the flux, the Casimir, and derivatives of the warping. And this is indeed is a hard equation. It's a hard nonlinear geometrical PDE, but we already solved it in the cusp. And luckily, in the bulk, we can use a different approximation. And in particular, it turns out that in the bulk, all the sources, except for the homogeneous flux, they die when going to in the bulk. There are various ways you can estimate it. For example, you can compute the contribution of these terms to the equation of motion by evaluating it in a numerical solution in the cusp, and check how these terms behave while you are going towards the gluing point in the bulk. And what you see in the slide, indeed, is the contribution of these different terms evaluated in the numerical solution of the previous slide. And as you see, all the terms die except for the flux. So what this equation of motion is telling us is that in the bulk, the Ricci scalar of the internal metric is positive and almost constant. And so to solve this equation, we need to find a geometry that realizes this. But luckily, there are no instructions to do so. And in particular, there is a theorem by Kasdan and Warner from 1975 that tell us that actually in any dimension of 3 or higher, You can take any function that becomes negative somewhere in your manifold, and for us, this somewhere will be the cusp. And this function can be the Ricci scalar of a certain metric in your manifold. And so for us, this function will be indeed negative in the cusp, where it will be the same function that solves the local equation of motion, and then it's continued to be constant, almost constant and positive in the bulk. And this theorem tells us that there is a geometry that does that, and so that solves this equation of motion. And this theorem actually tells us something more. We can what they show is that the metric that realizes this Ricci scalar can be taken to be conformal to a hyperbolic metric in the manifold. So what this is telling us is that this equation is only sourcing a conformal factor, but it's not changing much in the bulk the hyperbolic structure that we had before. And similarly, now you can ask a similar condition that come from solving all the other equations of motion. For example, for the equation of motion for the warp factor, again, it's a nonlinear PDE for this warping, but the same simplification applies in the bulk. Remember that we have already solved it completely in the cusp, and in the bulk, the same simplification holds because the other terms are similar to the one that we evaluated above. And particularly, this means that in the bulk, we have a simple Poisson equation sourced by the flux. And here, there will be some consistency condition for some global consistency condition that you get by integrating this equation in the wall manifolds compared to the bulk. And we'll use these conditions in the next slide. But other than that, there are no obstruction to solving it. And finally, there is another class of equation, another set of fluctuations you need to consider, which are the transverse traceless transformation of the internal metric. This will be another set of equation of motion, and as we have discussed in our paper, those are suppressed. So the deformation of the hyperbolic metric in the bulk is suppressed in the parametric regime we will work in, particularly because of this rigidity property of the Hessian around the hyperbolic metric being gapped by the curvature scale. Now, these are the conditions. Let's see how imposing this condition we can find an explicit family of these de Sitter vacua and what are the physical properties. And here, so the first thing you need to do is you start from a hyperbolic manifold. And here there is really a plethora of construction. There is a beautiful mathematical literature on hyperbolic manifolds. There are various ways you can construct them, from geometric ways to more algebraic ways. And here, what I would like to show is one specific family one can construct that has been constructed in this paper by mathematicians in 2021. And I like this particular construction because, in a sense, it's very simple. They tell us that in dimension from 3 to 8, you can construct hyperbolic manifolds, even starting from simple right-angle polytope in the upper half space. And to obtain a manifold, you need to do the following procedure. You start from a polytope. Here is an explicit polytope in dimension 3. And you have to prescribe a coloring of the faces of this polytope according to certain rules. And the second step is that you act with some reflections with respect to the faces of the polytope, acting once according to each color that you've chosen. And once you do that, you get a bigger polytope, still in the hyperbolic space. And then the next step is that you prescribe a certain identifications among the faces of this polytope according to certain rules that are inherited by the coloring. And once you do that, you get a manifold. And what they show us is that you can do it with these simple right-angle polytopes in dimension from 3 to 8, with 7 being the case that is of interest for us for the Sitter 4 in M-theory. And so for concreteness, let's stick with this class of manifolds. Once you have chosen such a manifold, one thing you have to do is to look at its cusp, and this is where we will need to glue the numerical solution with the Casimir contributing. And when you do that, you need to impose all the consistency conditions we have described before. So they have to do with the global consistency such that the equation of motion can be solved globally. And in particular, you have some integrated conditions, and such as, for example, also you need to impose quantization of the flux. And if you do that for a single manifold, well, you get a single de Sitter solution. But you can also do it for family of manifolds, so you will get in this way a set of some families of de Sitter solution if you do it for each member of the family. And what I want to show here is like a specific family that we have constructed, starting from these hyperbolic manifolds. And we are starting in this specific family, so let me describe it. If you take the manifold we discussed before, but before performing the gluing of the different faces, if you act with more reflections, let's say you fix one side and you keep adding reflection with respect to that side, And as a function of the number of reflections you make, you get a manifold at the end, an hyperbolic manifold, which has a volume which is 2 to the n times the volume of the original manifold before you acted with this extra reflection. So this gives you a parametric family of hyperbolic manifolds. And on each of these members of the family, you can perform this construction. And in particular, let's consider the case where you glue the single cusp, to the local numerical solution to one of the cusp, and you cut the other cusp short by using the filling procedure such that the Casimir there does not contribute. And in this explicit family shown here, what we have computed, so when you do that, you fix the local parameters of the local solution in a way that depends on the properties of the manifold. And in this explicit example we have done, and this fixes this gives you a way to extract the physical quantity of the de-Sitter compactification on this family. And in particular for this family shown here, we can compute that there is a parametric separation of the scales between the de-Sitter scale and the internal scale, internal curvature scale. We can also compute the cosmological constant on this vacua, in particular compared to the 4-dimensional Planck's mass, and we find it to be tiny and exponentially small in the number of reflections, so parametrically small in this family. And we can also check all the other consistency conditions. For example, we can check that we are parametrically away from the danger of needing sub-Planckian cycles, as well as the other integrated quantity that enter in the stabilization mechanism. But let me stress that this is one simple family that we started analyzing, but it seems here that there is a vast landscape to explore because there are many choices you can make at various stages of this construction. You can choose different hyperbolic manifolds, and those are quite explicit, and there is a vast space of those. For each hyperbolic manifold, you can construct these field geometries, and even starting from a single hyperbolic manifold, you can get infinite families of these Einstein manifolds with negative curvature. And there also you have other choices related precisely on how you do the gluing and which cusp are contributing. And so it seems that there is a vast landscape here to explore. And we started analyzing this in this work I briefly described. Okay, so let's now switch gears a little bit and ask following questions. So we've seen that with a combination of different approximation schemes in different regions, one can extract some broad physical quantities from this vacuum. But I think one natural question is whether we can actually solve the equations of motion in the full manifold in detail. Again, this is not really needed to extract the various broad physical properties as we have seen in the specific family, but I think it's a natural question, in particular, since we are seeing that we have these tools that are machine learning tools, as we've learned from Jim, that are very powerful. And in particular, we can also ask this question a bit more, we can try to be even a bit more ambitious. Can we actually directly solve this equation of motion for general Warper compactifications? And well, the problem is hard because the equation you have to solve are the one here in the slide. And these are indeed the equation of motion you get if you consider general compactification of a general higher dimensional theory of gravity. There are various ways you can rewrite this equation. For example, a natural way that I like is in terms of this so-called Bakrian-Ricci tensor, Ricci curvature, which is a way in which you can absorb the effects of the warping in a novel definition of curvature that turns out to be useful in various contexts. In particular, mathematicians have studied it in the context of optimal transport theory, where they've shown that if you can control this curvature, you can control the spectrum of certain Laplacian that turn out to be the same operators that give us the masses of the spin-2-Kaluza-Klein field around this vacua. So this means that this equation is not, when we solve it, it's telling us not just the property of the vacuum, but also of its fluctuations. But regardless of how you rewrite this equation, they're still very hard. They're still very hard also numerically because, for example, for 4-dimensional compactifications, we need to solve them in dimension 6 or 7, and standard numerical methods struggle in this dimensionality. But indeed, luckily, we have machine learning. And in particular, as we have seen, and we'll see also from Vishnu in the next talk, this has been as we found to be very powerful, for example, for solving for the Calabi-Yau matrix. And so a natural question here is whether indeed we can use this method to solve for more general matrix, not just for the matrix, but including in the Einstein equation directly the contribution of the flux and of the other physical fields and the warping. And so in these remaining few minutes, let me briefly describe how this will work. So as you've seen, we can use neural networks which are just parameterized functions. And a simple way to use neural networks to solve PDEs is by simply imagining to use them as an ansatz for the solution of the PDE. And then we need to find the correct parameters such that indeed we have a solution of our PDEs. And in the machine learning spirit, the popular way to do that is to construct a loss function, meaning that we construct a function which is minimized when we have found the correct parameters that solve our problem. And if you look at this problem from this point of view, it means that we have a different landscape now. We have the landscape of neural network parameters, and so we can study these in a sense as a physics problem, because now we have a landscape, and our goal is to prescribe a dynamics on this landscape such that if you start from some random initialization, we end up in a point that solves our problem. And so, because of this, I think that as physicists we can make progress on this problem. In particular, we can reinterpret the standard methods from a physics point of view, such as, for example, gradient descent, which is the most common method, gradient descent and relative, that people use. These can be thought of physically as some dissipative dynamics on this landscape that evolves while indeed dissipating energy, and then thereby stopping on critical points because of it has lost all its energy. But we can indeed think about other possible dynamics. One that we explored with Eva and other collaborators is the use of conservative dynamics in a method we call energy conserving descent, where convergence is due to kinetic effects, not to dissipation of energy. And because of this energy conservation, it means that there is a constant of motion we can track along the trajectory, and this gives us some analytic handle on the problem. And for example, in an upcoming work, we are showing that this is useful when you want to be more precise about the dynamics, for example, for application to scientific machine learning. Because a problem of scientific machine learning is that we don't just want to use machine learning to solve our problems, but we will also want to be able to put error bars on our method. And having such methods where you have more analytical control we're finding that it's useful for this problem. For example, we are testing on a problem of simulation-based inference in particle physics. But we think this is of broader applicability because of this general structure. But indeed, this slide is also meant to be an invitation for the community, the fact that we can use physics methods for this problem, and I think we can contribute more to this kind of field. And in the remaining few minutes, let me now go back to our original problem. So we were asking whether we can use machine learning to solve the equation of motion for general warped compactifications. This is a hard problem, and in a toy version of this problem, I'm showing that you can, at least in a three-dimensional toy example, it seems to work, meaning that you can find this field geometry I described before in these hyperbolic manifolds explicitly by directly solving the Einstein condition in the loss. So unlike the Calabi-Yau case, for example, here you're not employing a simplification coming from example for having the Monge-Ampere equation, but you can directly solve for the Ricci tensor. And it is useful in the sense that it allows to immediately add then the flux and the other physical fields. And in this simple toy version of the problem, indeed, I show that this indeed works in 3 dimensions. And but a three-dimension Einstein manifold is also locally hyperbolic, so this is not yet, I would say, very useful per se as a solution, but as a method, I think is showing that there is hope to scale now this procedure to a higher dimension. One can first scale, for example, in a higher dimension to solve the geometric problem, where, for example, in dimension 4 or higher, finding these field geometries explicitly, numerically, is still an open problem in hyperbolic geometry, and I think one can apply these methods. And also, then, a natural target is to go up to in dimension, say, up to 7, such that one can write down and find the explicit metric for the de Sitter compactification metric and other fields for the de Sitter compactifications I described at the beginning. And with this visual recap about the different landscapes we have talked about, let me thank you for your attention.
Thanks for the talk. Any questions, please?
Thanks a lot for a great talk. You covered a lot of ground, so let me back up and ask you to go back to the first part of your talk where
Yes.
you constructed de Sitter vacua. Do you have then a one parameter family? You had capital N in that example. you have a one parameter family where if you don't know the metric everywhere, you know it well enough in various patches to be sure that you have a solution and to be sure that the corrections are under control?
Yeah, so when we, depends exactly what you mean by sure, in the sense that what I'm showing here is that, okay, in the cusp, we have the numerical solution, you can go to whatever accuracy you want. And in the bulk, you have the hyperbolic metric. And when you study the other equation of motion, you will see that there are conditions such that you can perform this gluing. What I'm trying to show is that for some of them, we even have theorems that guarantee that they exist. But more broadly, even without the theorems, we can estimate that the correction indeed should be small. Having a theorem is a different question. It seems possible in this work in progress that you can actually do it. But even without the theorem, you can do these estimates. And in particular, if you are in the parametric regime I tried to describe, the correction indeed are suppressed. So also because here, like the metric then is smooth, the curvature is small, and the cycles don't get very small, so we don't think there are other corrections to this. And this is a specific family, a specific parametric family, but as I said, there are various ways we can construct this manifold, so maybe even more parameters to play with, not just one.
And in the specific family, how many cusp-like or smoothened out cusp-like regions do you have?
Yeah, so for this, and say this is a work in progress, so we just perform the gluing to one single cusp, but this manifold has many cusps. For example, before doing the proliferation, I think this manifold has like 4,000 cusps. When these get multiplied when we do this discovering. And here in this specific one, I'm assuming that I'm considering that for all the others, which is not the one when I'm doing the gluing, all the others are truncated by doing the filling procedure in such a way that we can truncate them to be very short. We can smooth them out with this mathematical procedure, attach the solid torus, such as very short, and Casimir doesn't contribute to that. And for one specifically, we are doing the gluing manually. But in principle, you can do it for all the 4,000 in different ways, and it will give you a lot of parameters to play with. But what I like about this kind of geometry is that it's very explicit. Like, you know the metric, you know these polytopes, you can play with it. But this is a work in progress. We just consider this simple family to start from. But that's why I think there is a vast landscape, but we haven't yet explored it.
Thank you very much.
Thank you. So if you construct these, so you use mostly the existence of metrics, and you're doing machine learning to construct them, but how do you know what are the light modes? What do you know about the solution to Laplacians?
So you mean after I found the solution, what can I say about the fluctuation?
There could be many light modes. Maybe for each cusp, you have a very light mode you're ignoring. How do you know they're
Well, in the cusp, we actually have computed the Laplacian because you can do it locally there and impose boundary conditions for the modes when you do in the bulk. In the bulk, there is the rigidity property. Like the fluctuation around the hyperbolic saddle points are gapped by the curvature scale. So we don't expect light modes there for that. Now, if you're asking whether we have a full second-order analysis of the full geometry, I don't have it. But there are no reason, at least I don't have reason to expect, because locally we don't see them in the cusp, and in the bulk we have this rigidity property.
Because in analogy with many examples, you have too many choices here that you usually don't have in
discrete choices.
Yeah, I know. You have too many discrete choices that you usually don't have in other string compactification. Usually, this means you get many light modes, usually. If you are saying no, in your case, that's different, it would be extremely important to check that.
Yes, I agree with that, yes. It would be important to check, but yeah, I don't see why they should arise here.
Thanks a lot, Bruno. This is super interesting. I wanted to ask about the, you mentioned a bit, but the Riemann, the higher additional corrections that you might have to, for instance, in M theory, you have this Riemann to the fourth corrections.
Yes.
And presumably to give these estimates, you had to compute what were the A and B warping factors you were telling us about. Did you estimate what the size of the Riemann to the fourth is relative to the other terms?
Yeah, so for example, you can do it, I would say that the most important part of the geometry where you have to do that is where there is a strong variation of the fields, like in the cusp. And here we computed those explicit in the cusp, and those are indeed suppressed. This is an explicit solution over these. You can just compute those tensors. And those are
but even in the bulk piece,
okay.
the Riemann to the fourth is smaller than the Casimir and the curvature. It's not more important than the other.
No, I think it is not. In this parametric regime, it's not. Like you can be away from that. Yeah.
Thank you. Very nice talk. Where do you put the standard model here?
Okay, one step at a time.
No, but I think because in Calabi-Yau we know how to put it.
So I think one can engineer, like, for example, particle physics. For example, one has a disposer like branes here, like M5 and M2. We haven't considered those yet. Very preliminary one thing I could say is that, for example, you can, if you take an M5 brane, at least we just analyze what happens with one. If you take one and you take it to be space filling, and then you're wrapping two of these two cycles of this local transverse torus, it seems that there is a minimum for its potential in the cusp. So we estimate, compute the potential for an M5 sitting in the cusp, and it could stay there. Like there is a stable point where you can put one. But we haven't really thought about particle physics yet. It was just some very preliminary check. But the point is that, for example, in the cusp, you have a lot of volume in the cusp, and you have an explicit solution. So there you can try to do this you can ask these kind of things. But I don't have anything more precise to say about it.
That's fine. Okay, thank you.
Great. Thank you very much for that talk. And on that note, we'll move on to standard model, possibly, with Vishnu Jejjala. Thank you. Let's thank
All right, so let me, am I mic'd? Let me start by thanking the organizers for a fascinating and wonderful conference, and of course the invitation to speak here. So I can tell you today about Calabi-Yau metrics and Yukawa couplings and an approach to precision string phenomenology. So this is work done in collaboration with Per Berglund, Georgi Bitbaya, Tristan Hubsch, Damian Mayorga-Peña, Challenger Mishra, and Justin Tan. Damian and Justin are both in the audience, and you can, of course, corner them for questions as well. So I'm addressing a problem that's several decades old, is to deal with what can we say about explicit string compactifications in heteronic string theory. So we know that we can get a large number of four-dimensional n=1 effective field theories with chiral matter from compactification of the E8 cross E8 heteronic string on a Calabi-Yau threefold. So I'll remind you that Calabi-Yau is a complex Kähler manifold that admits a Ricci flat metric when the first Chern class vanishes. And depending on the rank of a vector bundle you put on top of the Calabi-Yau, you can have the E8 symmetry being broken to E6 or SO10 or SU5. You can break the gauge symmetry further by introducing freely acting Wilson lines, and this is the textbook paradigm for model building in particle physics ever since Candelas, Horowitz, Strominger, and Witten in 1985. We also know that there are 500 million four-dimensional reflexive polytopes, triangulations of which give us desingularized Calabi-Yau threefolds, which we can use for model building in this manner. We'd like to understand aspects of what we can say about what happens to the effective field theory when we choose such a Calabi-Yau threefold. So the goal is to pursue this understanding of this low-dimensional theory based on the geometry of the Calabi-Yaus. So as in our first course in quantum field theory, we'll recall that the kinetic terms live in the Kähler potential and the interactions can live in the Seward potential. Topological data out of Calabi-Yau and the bundle structures we put on top of the Calabi-Yau is enough to tell us about what fields are present in low energy theory and what interactions are present as well. We do not know from this or what the couplings are, how strong the interaction strengths these various fields are, and in order to figure that out, we need geometric input as well as the topology. So in particular, these lambda ijk's are the Yukawa couplings, which tell us how strong the fields interact. And in general, to calculate these, we need to know the Calabi-Yau, the bundle structures we put on top of the Calabi-Yau, and the Ricci flat metric on the Calabi-Yau geometry. The Ricci flat metric is unique for any complex structure in Kähler class. So why do we need the Ricci flat metric? Well, the Ricci flat metric is one which solves leading order vacuum equations of motion in this setup. And for purposes of phenomenology, the Ricci flat metric is needed to normalize magnetic terms that appear in the Kähler potential for matter, and then to compute the Yukawa couplings in general hydraulic compactification. Further, for things like moduli stabilization, alpha prime corrections, we need to understand the metrical structures of these geometries, and perhaps depending on the mechanism of supersymmetry breaking, we need the metric for that as well. So Ricci flatness by itself is a system of fourth order nonlinear partial differential equations, just setting RAP equal to 0 in this context. This is equivalent to a second order Langevin pair system, and this is essentially the content of Yau's theorem. So to date, the best we can do for Calabi-Yau n folds, n is bigger than or equal to 2, is numerical approximation in the general setting. So we'll develop these numerical approximations in the course of this talk. So how to approximate a Ricci flat metric? The initial work in this direction was to solve the Langevin pair equation directly. So Hedrick and Wiseman used the Gauss-Seidel method in order to find approximations to the Ricci flat metric in this manner. And they did this on various K3s. Slightly later, Donaldson provided an algorithm to provide a so-called balanced metric that in some particular limit converges to the Ricci flat metric. And there have been various implementations of this Donaldson algorithm in order to find numerical Ricci flat metrics on Calabi-Yaus. This procedure is an iterative procedure. It starts with the pullback of the Fubini-Studi metric in the ambient projective space in which we're considering our geometry. And the idea is then to start from that seed and build the process of finding a flat metric up iteratively. The difficulty is that at each level in this procedure, you need to look at the degree k degree k polynomials in the variables that are available, and this grows polynomially. So for example, for the quintic, this grows like k to the fourth. So very quickly, if you're doing numerics in this manner, you run into issues. The more modern approach now, since essentially the COVID years, is to use neural networks. This program was initiated by Ashmore, Hay, and Overett, who actually used neural network techniques to improve Donaldson's algorithm. But the various collaborations worked on finding a more direct approach to the Ricci flat metric in late 2020. So as we saw in the last talk, one way to find the solutions you're after is to engineer a loss function that vanishes on the locus of solutions that you want. So in particular, we essentially look at a loss function which is of the form absolute value left-hand side minus right-hand side for some system of equations. So one thing we could do, since we're after Ricci flatness, is just look at the absolute value of the components of the Ricci tensor and set them equal to 0. However, derivatives tend to amplify error. So this is not the most efficient way of doing things. A cleverer way of doing things is to take the volume in a metric-independent form and the volume in a metric-dependent form and compare the two, and that way you have something which looks like left-hand side minus right-hand side. So morally, this is what we do in measuring the flatness of the metric. We have a metric-independent expression for the volume and a metric-dependent expression which involves the 1-1 Kähler form. Other conditions are necessary in the loss function as well in order to ensure that we maintain the closedness of the Kähler form, compatibility in coordinate patches as we're working with points on a manifold explicitly in some coordinate atlas, and they remain the same Kähler class. The last can be achieved using Kähler-Ricci flow, which is guaranteed to preserve the Kähler class. We've been able to get this to work really well for the torus, but for anything more complicated than a torus, the numerics that we obtain from Kähler-Ricci flow is much inferior to the numerics we obtain from neural networks. Another way to remain in the same Kähler class is to just find a phi that connects the Fubini-Studi seed metric to the Ricci flat metric the one is after. And the trick is to find a phi that's globally defined that does this, and the CY metric package by these authors was to first implement this idea. Next, since we're working with points on a manifold, we should choose points in a fair sort of way. And the idea for how to choose these points was provided by Shipman and Zelnick. The idea is that we know, for example, for a complete intersection Calabi-Yau, it's embedded in a product of projective spaces. We know the metric in projective space is the Fubini-Studi metric, So we choose points with respect to the Fubini-Studio metric in the ambient projector space, draw lines between them, and see where they intersect the Calabi-Yau. Now we'll notice that if you look at two different forms of the quintic, the Fermat quintic in P4 and the Dort quintic with the parameter here being 1, the distribution of points you select is very different. So the point selection is a crucial aspect of finding the Ricci flat metric that we want. So the best architecture for finding a flat metric we have today is what we call a spectral network. The idea is to take points in the manifold and write them in a way that's C-star invariant. This pre-processing gives us the so-called spectral layer, and we further divide these matrix elements into real and imaginary parts, and then we feed it into these neural networks of the type that Jim described in his talk. So the idea here is to learn this function phi using the spectral network in order to find the Ricci flat metric starting from the seed metric. So as an example, if you look at K3, we look at the quartic in P3 together with a sum of quadratic squared, we find that this so-called Cephalou pencil is singular for particular values of lambda, and these singularities, you have 8, 16, 12, and 4 singularities of A1 type at these special points. So if we use kind of the 5 points for training, and we look at lambda equals 0, so we ignore this, this quadratic squared piece, we just look at the Fermat piece, we find that the spectral network performs really, really well in finding the flat metric compared to the other alternatives. This performance is equivalent to about k equals 8 in Donaldson's algorithm. If you look at the singular points, so lambda equals 1 was one of the singular points, we find that the spectral network also performs reasonably well. The other singularities at 3/4, 3/2, and 3, and lambda equals 1, we find that the one way to assess the performance of the neural network is to take a geometric quantity and use this to compute a topological quantity, which we know the answer. We know the Euler character of K3 is 24. We find that away from the singularity, we do get 24 with our Ricci flat metric that we obtained numerically, but the performance is not so good near lambda equals 1 and lambda equals 3 in particular. The lambda equals 1 singular geometry, this is the Kummer surface, and this is where there was a analytic metric that was written down. Unfortunately, our numerics isn't really good enough to compare the analytics in this particular case. So that's the introduction to finding Ricci flat metrics. Now I'll start applying these Ricci flat metrics to the problem of finding Yukawa couplings in a string compactification. So I'll remind you that the low energy matter spectrum of theory, you have charged matter multiplets. They're counted by H1 of V and H2 of V, where V is the vector bundle on top of our Calabi-Yau. So we'll specialize in the case of E6, which is the commutant of SU3 holonomy in this E8 we started out with. So we're looking at E6 gut theories. And the 1-1 forms and the 2-1 forms correspond to the number of generations and anti-generations in our theory. The Yukawa couplings of the 1-1 forms, these are topological, so we know how to compute these. And the 2-1 forms, these are quasi-topological. So what this means is, given a 2-1 form, we can use nowhere vanishing top holomorphic form to write a 0-1 form that's equivalent to the 2-1 form. And we can write down unnormalized Yukawa couplings, which are corresponding to the 27 cube couplings in low energy effective theory. Quasi-topological as context means this calculation depends on the cohomology class, but not the actual representative. But this is not the coupling that's physical that we'll measure in that'll appear in the Lagrangian. So we want to turn this unnormalized coupling into a physical coupling that will be the parameter which appears in our low energy theory. So to normalize Yukawa couplings, we start with these unnormalized couplings and we perform this normalization. Generically, these normalizations are computed using an inner product that depends on the Ricci flat metric. So we define an appropriate orthogonal basis for H1 of V that enables us to perform these normalizations. So in particular, there is a trick that we can sometimes use, special geometry, in order to avoid this calculation. And we'll use the special geometry trick to benchmark how well the neural network is performing. So in the standard embedding, because normalization turns out to be computed independent of the Ricci flat metric, only requires the metric on the complex structure moduli space, the Yukawa couplings will be the same in every Kähler class. So standard embedding just lets the holomorphic vector bundle on top of the Calabi-Yau that solves the Hermitian-Yang-Mills equations just be the tangent bundle. So the metric on the Calabi-Yau does double duty as the fiber metric, since we're looking at the tangent bundle. This is the case which is a textbook case. So it's this case for which the number of generations of the theory is given by the index of the Dirac operator, which is given to us by 1/2 of the Euler character. So this is the standard classical framework for heterotic model building. Deformations as vector bundle correspond to the complex structure moduli of Calabi-Yau, and the metric of the complex structure moduli space is the Weil-Petersen metric. So using Weil-Petersen geometry, we can compute the Yukawa couplings without knowing the Ricci flat metric, and we'll in fact compute these Yukawa couplings in 3 different ways, 2 of which invoke Weil-Petersen geometry, and 1 of which is using our machine-learned Ricci flat metric on the Calabi-Yau. So the first way is performing period integrals. This is due to Candelas, Delosa, Green and Parks, and Morrison in 1991, and we obtained the Weil-Petersen metric by finding certain quantities to satisfy the Picard-Fuchs equation. The analytic result of period integrals gives us an analytic expression for Yukawa couplings and Weil-Petersen metrics. However, this is only practical for a small number of H21 moduli. So it's not practical when H21 is large. The other methods I'll describe, these work for any H21 fairly well. The second method is Kodaira-Spencer geometry. We take a base point and we look at the tangent to the deformation space of this base point, and when there's a Kodaira-Spencer map, which sends it to the cohomology group associated to vector fields on this Calabi-Yau. And then we consider transition functions that we augment with these deformation parameters, of which there are H21 of these. And then we can basically construct this Kodaira-Spencer map explicitly. And it turns out the Weil-Petersen metric, which typically invokes the flat metric, can be determined without knowledge of the flat metric. And this is an expression we have then for this Weil-Petersen metric, and the Weil-Petersen metric will turn out to be the metric we use for normalizing the fields that appear in the Kähler potential. We can as well use machine learning in order to learn the Yukawa couplings that we're after. So again, we start from the harmonic projection, and we find some smooth section of the tangent bundle such that the thing is harmonic. So in particular, the harmonic projection minus the element we started out with, this differs by something related to a smooth section of Tx. So the strategy is to model this section of the neural network using a machine-learned Ricci flat metric. We start with an over-complete basis of sections. We parameterize the coefficients to get a globally well-defined object. A similar strategy is employed by Douglas and collaborators to study a similar problem to find harmonic one forms on G2. And similarly, these guys, Constantine et al., started looking at non-standard embeddings using this kind of technology. In principle, this applies to any holomorphic vector bundle on a Kähler manifold. And the idea then is to just, given some reference form, we machine learn the coefficients which are needed to ensure that the form we're constructing is harmonic. The loss function essentially guarantees the harmonicity of the form. And again, these methods apply to any H21. So I'll show you some pictures of results. This is the quintic. The Fermat quintic is this expression with size set equal to 0. And what I've plotted here is the phi, which is machine learned. So the colors indicate how strong phi is at various points on some section of this Fermat quintic. If we look at the Dwork quintic, where we have the psi parameter turned on, and I look at the mirror of the Dwork quintic, I flip the roles of H11 and H21, and I look at the psi, and I see that the period integrals matches the Kodaira-Spencer map I looked at. At a particular point where psi equals 0, the Fermat point on its mirror, the loss function enables us to find a harmonic representative. This can be computed using period integrals, and the machine learned result essentially matches the result for the period integrals. As well, for a special point in the quintic moduli space, the Gepner point, we can compute the Yukawa couplings as powers of kappa. This was calculated by Distler and Green. We find a diagonal Bob-Pearson metric upon our normalization, and comparing the expected values to the numerical values we obtain, they're on the nose. So we find that in this particular case, we're able to calculate and reproduce Yukawa couplings that appear in the literature in the old heterotic days. We look at another manifold, the 40 quadrant, is defined in terms of these defining equations. I'm looking at the Kretschmann scalar here, and looking at the Kretschmann scalar both in the Fubini-Studi metric that we start out with and the Ricci-flat metric in machine learn. We see these histograms for this Kretschmann scalar are different in the two cases. So machine learning is actually accomplishing something. Moreover, if we look at the two different Kähler classes associated to this geometry, we find it's learning different things. And if we define the same Kähler classes in different descriptions, the histograms are roughly the same. So we're learning the appropriate metric in each Kähler class. Next, we'll look at the intersection of two cubics. These are the defining equations here. We find the Bob-Pearson metric, and for the normalized Yukawa coupling in these cases, the calculation using the period integrals and the numerical Bob-Pearson metric we obtain with the Fubini-Studi from the Kedara-Spencer map. These will agree. And if I look at a section of this, I find that I can calculate these quantities in various different ways. Period. I can use a non-harmonic representative using the Fubini-Studi metric rather than machine-learned Ricci-flat metric. I can use Kedara-Spencer geometry. I can use a harmonic representative appropriately with the Ricci-flat metric I've learned, or one which is non-global, and I find that the harmonic representative, which is machine-learned, special geometry, and the analytic period all agree. And this agreement persists even close to singular points in this complex structure moduli space. So at certain points, it seems that the Fubini-Studi approximation is not so bad, whereas at other points, it seems that the machine-learned approximation is needed. So these are the Yukawa couplings for the same theory, and again, we find that the agreement persists even very close to the singular points in the geometry. One more example is Tian-Yau. So we have this manifold, which is P3 cross P3, in which we embed a cubics and a bilinear. This admits a freely acting Z3 quotient, which reduces the Euler character to -6. Because this is -6, Green, Kirkland, Myron, and Ross used this as a candidate for phenomenologically realistic model building. The model which I'll look at is due to Kalara and Mahabatra, and this is an SU3 cubed model with 9 leptonic fields and 7 quarks and anti-quarks. The Bob-Pearson metric along one direction of the moduli is shown here, and the unnormalized Yukawa couplings were calculated by Candelas and Kalara, and these error bars are associated to errors in Monte Carlo integrals, and we find the unnormalized Yukawa couplings agree in the literature and also the calculations that we do. Normalization was not done previously. So when we normalize these Yukawa couplings, we see the physical Yukawa couplings in this theory, they shift quite a bit upon normalization. And these are the leptonic Yukawa couplings in this SU3 cube theory. If we look at how the Yukawa couplings change as a function of the moduli, we see that starting from a symmetric point in moduli space where this epsilon parameter is 0, moving not very far in this complex structure moduli space, we see hierarchies developing as we move away from these symmetric points. So hierarchies in Yukawa couplings, at least in certain string models we've looked at, are not so difficult to attain. So this is promising for model building when you compare it to particle physics that we see. As well, we look at couplings between these leptonic type fields and quarks and anti-quarks, and we see that there are singular points in this moduli space, and close to the singularities, the machine learning of the harmonic forms works reasonably well. We also find that As you move away from these singular points, but not very far away, we see hierarchies developing again in these Yukawa couplings. So this is again a promising signal that the kinds of things we want to see in particle physics are achievable in heterotic compactification. So we've put out a library of code that enables these calculations I've shown you. It's available by looking at this website here. There are other packages that other authors have developed in the same context. So Douglas and collaborators has ML geometry, Larfors, Lucas et al. They've got CY metric. Krippendorf and collaborators have CY JAX. They're all rather similar, and they do similar calculations. Let me show you an example. So this is taking the quintic, the dwarf quintic, and I'm selecting 100,000 points, and I'm training to find the Euler character using the integral of the Euler density, and I get minus square root of 2 when I do this, as I should get for the quintic. And as you see, I sped up the code by a factor of 20, but it's fairly efficient in finding this result. So let me conclude with a prospectus for what's to come and what other groups are doing and what we're thinking about. So the first takeaway message of this talk, I hope, is the precision string phenomenology, this heterotic context, is possible. So one thing to do is to look at things which is not the standard embedding. Already, Constantine and collaborators have looked at this for sums of line bundles on top of a Calabi-Yau, and they've computed Yukawa couplings in this context. As was mentioned in the previous talk, this collaboration has also started looking at alpha prime corrections to Calabi-Yau geometries. We're interested in toric Calabi-Yau manifolds in addition to the complete intersection Calabi-Yau manifolds I talked about in the bulk of the talk. The machine learning methods are less effective for the toric manifolds than they are for the complete intersection manifolds. They'd like to improve that state of affairs. People have started looking at G2 manifolds and SG2 structure manifolds using similar tools. Now that we have metrics on Calabi-Yaus, we can start addressing ideas like small planet distance conjectures using these explicit metrics, and these guys have started doing that. We're also thinking about using these ideas in type 2, in addition to heterotic, with the goal of understanding cosmological issues as well. And then, of course, the grand goal is to see whether standard model building is possible in this context, and we can test whether the standard models that are proposed in heterotic string theory are anything like the standard model that we see in nature. One way to improve the performance of these machine learning efforts is a better point selection scheme. And this is something we're trying to technically improve in this pipeline that I've described. So here, I've shown points selected on the torus using the Fabuni-Studi metric as our seed. And I've chosen points selected using the flat metric, which I know analytically on the torus, as our seed. If I start with the second distribution of points, and I start learning with the pullback of the Fabuni-Studi from the ambient space, this choice of points works much better in finding the flat metric than this choice of points I've been using previously. So there could be some improvement in point selection that really speeds up the process of finding flat metrics and improves the quality of the flat metrics that we do find. So this is something which we're thinking about. Also, since we've seen intriguing possibilities for analytics, at least in certain forms of K3, the Kummer surface, we might try to improve this analytics in a more global sense. And we know that, for example, when you make the complex structure large, in the XYZ limit, we should see torus vibrations. We can start looking for these torus vibrations and then try to bootstrap a way to find analytic metrics based on this. So thank you for your attention.
Thanks for the very nice talk. Questions? I think I'm closer.
Thank you. Very nice talk. So, two questions. In the case of orbifold limits, where we do know the exact metric, if you use your methods and deform towards that, how close do you get to the known metric? For example, for K3, for T4 mod Z2?
So the T4 mod Z2 point is the one that I didn't do very well at. This is lambda equals 1.
With lambda equals 1 is that? And how well do you do there?
So we looked at this the Cephalou form. So the singularities are 3/4, 1, 3/2, and 3. The singularity at 1 is T4 mod Z2 basically.
Oh, okay.
And that's the one where we performed worst as far as our machine.
Worst, you said?
Yeah.
I see.
And this is also where there is some analytic thing we can maybe compare it to, we can do better.
Yeah, so my question is, can you use the fact that we know the exact metric there to improve your method?
I haven't tried. It's possible. It's a good idea. We should try.
And the other question is that can you use your methods to calculate the spectrum of Laplacian of various forms?
Yes.
Have that been done? Has that been done?
The people who've been doing this are mostly Ashmore and Rula, but they've been working on similar ideas, yes.
And how good are they? How accurate? Can you assess how accurate they might be?
They find that, well, they've been using this in the context of these small planet distance conjectures. They're finding there are light modes that seem to appear as you move along geodesics.
How accurate are they?
I don't know.
No, okay. Thank you.
Any other questions?
Very nice talk, Vishnu. I missed your comment when you were saying that you were getting Yukawa couplings to behave in the way that we like phenomenologically.
So what I was saying was that if you move, so 0 is a symmetric point in this space. You move away from the symmetric point by turning epsilon to say 2, I do find hierarchies developing.
Hierarchy couplings, so I used to have a hierarchy of masses in the
I haven't converted these couplings into masses, but I see hierarchies in the Yukawa couplings.
I mean, just you mean to the idea is to fit with the hierarchy of masses of different generations as well. Yeah. Okay, that's good. Thank you.
Thanks, nice talk. I'm following a bit on that. So how about modular stabilization? Sorry. I guess here you want moduli to be stabilized at a given point. Do you see any way of
doing
doing
anything
it?
with moduli stabilization yet. But that is the goal, that we find some nice points, we find some ways to isolate ourselves to those nice places in moduli space.
Yeah, this one went from Juan.
Yeah, so I think in one transparency you had a comparison between something you computed at the Gebner point and then something you computed using geometry.
Yes, so...
I thought the Gebner points were not geometric, or am I confused?
I think in this particular model, Dissler and Green showed that the Yukawa couplings at this particular point are powers of this kappa. So we just took this particular point and we looked at, I think these are using Kodaro-Spencer maps to find the appropriate Yukawa couplings to normalize there, and we find agreement between what's in the literature and what we calculate. Okay. Yes. I see.
Great. If there are no more questions, let's thank Vishnu again. And that concludes this session. And Fernando, some announcements.
Yes, thank you. Yes, just to remind you, in 15 minutes at 6 p.m. sharp, we'll start the general public talk by Steve Schenker. So if you want to stay here or come back, it's okay, but there will be a lot of people coming who are not physicists. So, and if you're leaving your backpack, just probably it's better to take it with you and then come back. I think after